Alright, hey, today is the follow-up video to the voltage division circuit. So today I'm going to do current division. I'm going to draw an example circuit and then derive how you can express the resultant currents in a parallel circuit relative to a source current. So give me a sec to go ahead and draw that up. Okay, so here we have our general form canonical current division circuit. It's a source current with two circuit elements in parallel. And unlike the series case where every element shares the same current, these elements are in parallel, which means the total current is going to get divided up between the two elements. And the dual is, in this case, each element shares the same voltage. So the source provides a current, and then dependent upon this load here, some resultant voltage will appear, but it's the same voltage across each element because their nodes are shorted together. And as we already know, they're in parallel, and this is a phenomenon that you see in parallel circuits. So then the question becomes, depending on R1 and R2, exactly how much current flows through each resistor, and what is its relationship to the source? So how can we derive a formula or an expression that relates the current I2 to the source current? So the first thing I would do is say, well, we know by Ohm's law that V equals I2 times R2. And I could have written V2 here, fine, but V2 equals V1 equals just V from the source, so I'm just going to go ahead and keep it like this. And therefore we can say that I2 equals V over R2. Okay, great. So yeah, of course, if we want I2, we can just take this ratio of the voltage across R2 to its resistance, and that will tell us R2. But what that leaves us with is we need to figure out the total voltage that appears across the entire parallel circuit. And to do that, we need to actually know what this total equivalent parallel resistance is, because we know the current, we want the voltage, so if we can identify this total equivalent parallel resistance, we'll know exactly what the voltage is as a function of the source current. So a few videos back I talked about how to calculate equivalent resistance in parallel. So let me go ahead and write out that formula. For the case of two resistances, we know that the equivalent resistance is equal to 1 over the first resistance, R1, plus the second resistance, well, 1 over the second resistance, R2. And in the case of two resistors, this expression simplifies to something kind of cute. It's just R1 times R2 divided by R1 plus R2. And if you think about that, if you just add factors of R1 and R2, multiply through the top and the bottom, you'll get this right here. And this is only true for the case of two resistances. So if you have three, it's not R1 times R2 times R3 over the total sum. The formula, the expression becomes more complicated than that. But in the case of just two resistances, it's nice and short and sweet like this. And so you can just remember, oh, it's the product over the sum of the resistances, and this is probably the fastest way to calculate this, just back of the hand, or if you have your calculator. And this is easier to think about than this inverse over the sum of inverses. But they're equivalent. And another, I guess I'll go on a quick tangent. When you have resistances in parallel, you can have any number of resistances in parallel, and you can treat them as combinations of pairs of parallel resistors. So if I have three resistors in parallel, I can just look at two of them and treat that as two, find some equivalent parallel resistance for those two resistors, and then now I'm left with only two resistances. So you can just work two resistances at a time. You don't have to write out an entire formula for any number of resistors. And same thing in series, because resistors just add in series, right? And this is you're just adding numbers at that point. So if I'm adding up 10 numbers, I don't have to add them all at once. I can add the first two and then add that to the third one, and then I can just add one at a time. And so that same concept applies with parallel resistances. You can just work two resistors at a time, and it allows you to use this nice, cute formula. Now that we have the equivalent resistance, we can actually write an expression for the total voltage, which by Ohm's law is clearly I, the total source current, times this, well, I'll just write Req. So V is I times the equivalent resistance of the circuit. So great, we have an expression for V. Now if we look back at our expression for I2, I'm just going to substitute in the V here. So therefore, I2 equals I times Req divided by R2, which comes from this here. And now if we substitute in, again, the expression for the equivalent resistance here, you'll notice that the R2 is going to divide out from that. So our final expression for this current I2 is going to be equal to the source current times R1 over R1 plus R2. And pause for a second and think about how similar this looks to the case of voltage division. We have a ratio that takes exactly the same form as the voltage division case, and we have the source current here, which would be analogous to having the source voltage here. But there's one kind of subtle difference, and that's that in the case of voltage division, if this was V2 and this was a series circuit, if you just remember back to the other video, the magnitude of the voltage depended upon the resistor that voltage appeared across. So in the case of voltage division, the bigger the resistor, the bigger the voltage that appears across that resistor. But in this case, the current I2 is actually directly dependent upon the resistor R1. So the current I2 is dependent upon the resistance that it doesn't flow through. And that seems kind of weird, but if you just think about, how current flows and the physics behind Ohm's law, it makes a lot of sense. So it becomes clear when you start thinking about the limits of these resistances. So if you have some resistance R2 and then let R1 get infinitely large, well, you know from Ohm's law that I2 is the ratio of the voltage and the resistance here. So if you just look at Ohm's law here, well, as R goes to infinity, this expression goes to 0. So yeah, if you have an infinite resistance, no current can flow through it. So the bigger and bigger and bigger R1 gets, all the current's going to flow through R2. And this is exactly what we see here, because as R1 goes to infinity, this ratio approaches 1, and then I2 is just the source current. And so what I'm saying is, in that example, this is just the limit at which R1 goes to infinity, and the circuit simplifies to just a single resistor. And you could do the same thing for I1. I mean, if you wanted I1, and I guess I'll just write it out, it's the source current, except it's dependent upon R2. So as R2 were to go to infinity, then the circuit would reduce to just R1, and the entire source current would flow through R1. And so there's a lot of parallels here to the case of voltage division. So I encourage you to think back to the video that I did on the voltage divider circuit, and just think about how similar these two are. They're dual concepts. One's a parallel circuit, one's a series circuit. A lot of times in electrical engineering, it makes sense to talk about series circuits in terms of voltage, and a lot of times it makes sense to talk about parallel circuits in terms of current, which, if you notice, I'm using a current source here rather, whereas in the voltage division case, I was using a voltage source. And this is just a pedantic device, so there's no reason this has to be a current source. You know, you can have any kind of source, and the division will still take place. It's just very easy to talk about and think about when you use a current source for parallel circuits and when you use a voltage source for series circuits. But anyway, I'm thinking, and by the way, I did this in the last video, so I won't do it here, but you should verify that the sum I2 plus I1 actually gives you I, or rather that these currents add up to 1, or this ratio R1 plus R2 divided by the sum that actually adds up to 1. And I think you can do that fairly easily. So I think now I'm going to leave the video here, and I'll start preparing for the next one, in which I'm going to try and introduce the concept of node voltage analysis. But before I do that, I might have to talk about ground, because I don't think I've introduced that yet, and it makes things a lot easier. So that's, yeah, some such video with that sort of flavor will be coming up next. Anyway, I hope this was helpful. Let me know if there's anything I can do to improve. Thanks again for watching, and I hope you guys have a great day.